Okay, thank you, David. Thanks, Carl. And it's nice to know about this great forum. I'll try to join from now on. I guess the relevant part of my CV for this talk is indeed that Tali was my PhD advisor. My PhD lasted quite a few years, so I had the pleasure to work with him closely, and I learned a lot over the years. Certainly had a strong presence in my life, like for many of us. And I think, you know, when I think of Tali, and I think many of us, I distinctly remember many of his talks. I think hearing him speak about science was always an exhilarating experience. And I think the words that David mentioned, enthusiasm and passion, are really, you know, I keep hearing them when talking to people about Tali recently. So I think he was indeed very passionate about his work, really committed and ideological scientist, I would say. And it was really, you always learn something new from hearing him talk about his work. So yeah, it's hard to get used to the idea that he's not around anymore, and we truly miss him. So I think, you know, given what I said, I'm not going to attempt to talk about Tali's work here. I think no one does it or did it better than him. But I did, so I will talk about work in my group that in a way corresponds with some of the ideas that he worked on, and I'll describe it. But I thought it'll be nice to, you know, put up this video. I think probably a lot of you have seen. I think this really captures Tali's, you know, view of science to capture a theory. You know, this was part of his thinking of deep learning in terms of information theoretic measures. And I think it's so beautiful that there's this video that you could probably, you know, understand very quickly the story, and it captures a very elegant and deep theory of what's happening in learning, and deep learning in particular. I think it was very fortunate that Tali, you know, in the last 10 years or so of his career, everything sort of came together in this miraculous way. He's thinking about information, the information bottleneck, with these you know, deep learning algorithms, and this idea that actually when neural networks learn, artificial networks learn, they sort of capture this trade-off between information and compression. So the idea in this video, in just a few words, is that when a network learns, say, a mapping between X and Y, it first sort of tries to figure out what the mapping is, but then it tries to forget anything that's not necessary about the input. So it sort of compresses the input, tries to forget about it. This is the left-leaning tendency here in the later part of training, of learning. And this really nicely captures this idea that the network is trying to simplify and not remember things about the input that are not needed. So yeah, I think a beautiful illustration, a theory that's really you know, impacted the way a lot of people think about deep learning from the theoretical perspective. I had the pleasure of reading, you know, what people have said about this in recent days, and I think it's clearly had a great impact on the community. Okay, so I guess this is, in a way, a starting point for what I want to talk about today, is this idea that networks, that learning algorithms try to find simple explanations of the data that they're trying to learn. Okay, so I'll describe the problem and give some of our work in this context. Okay, so just to, you know, so we're on the same terms, I will talk about deep learning. This is something many others are interested in. So deep learning, you know, from its theoretical or sort of performance perspective, is something simple. It's the idea of using multi-layered artificial neural nets or some function class to learn mappings between some input and output. Okay, and it works tremendously well in practice. as you all know, for vision, for language, for games, so some examples of face recognition and Go. So this really works, okay? And the protocol is actually also beautifully simple. So if you wanted to use this, if you want to explain to a student how you do this, it's very simple. First, you collect data. So say you want to recognize the content of images. So you collect data with images and their labels. You say this is a corn, this is an apple, etc. Then you decide on some network structure. So a network, again, some function that maps from X to Y. And it's just a sequence of layers where each layer is a linear transformation and a pointwise nonlinearity. So you decide on the structure. All these edges are parameters to be learned. And then you optimize. Namely, you find the parameters of the network that best fit your training data. So this is basically the protocol, right? And with this, you can learn to map, text to meaning, images to content, X-rays to diagnosis, etc. And it really works. Oh, and I forgot about the last step. The most important step is once you train the network, you use it on new data, right? So now there's a new image. It wasn't in your training data. You want to know what's in that. You show it to the model that you learned, and it says, it's an apple or whatever. Okay. Okay. So this is the protocol, and it works. Oftentimes it works. So again, the practice is you take these networks. I forgot to say they're typically huge. Namely, they have millions of parameters. And the way you optimize them is using a very simple optimization algorithm that you learned in the first class of optimization courses. Is gradient descent. Namely, you go in the direction of steepest descent of your objective. You start out from some parameter and then keep improving your loss. Okay, so that's the practice. Okay, and of course we want to understand why this works. Because it's interesting and because we want to maybe build better algorithms, right? So, from a theoretical perspective, if you look at sort of worst case theory, none of this should work at all. Why? Because the optimization problem that you solve, the training problem, is non-convex. Namely, in the worst case, it could be, like this egg cartoon that we see here. There could be many bad local minima, and this very naive gradient descent algorithm could easily get stuck in one of these. Okay, so it's not at all clear why you can find a model that fits the training data well. The other problem is, if you go to a statistics 101 course and you say, I'm learning a model with millions of parameters and I'm using like 10,000 examples to train it on, then you could obviously overfit, right? If you have few data points and a lot of degrees of freedom in your model, then the model can fit the data in wildly different ways, and there's no reason to expect that you'll be able to learn anything beyond your training data, right? Okay, so these are sort of two serious theoretical hurdles, which sort of lead to the question: why does any of this work at all? It could fail in any one of these two hurdles. But in practice, when you train large neural nets on your data, you often get to low training error, okay, often even zero. So it seems like this non-convexity is somehow not an issue. You don't get stuck at bad local optima. And perhaps as surprisingly, the models do not overfit. So you have these huge models that are trained on not that much data often, and they generalize well. So when you show them new points, for example, if I show them this point here that's not in my training data, it will somehow find something that is close to the truth, okay, the true function, which is also rather surprising, okay? And the big questions are why, right? So there's quite a bit of work nowadays on theory of deep learning, which in a sense asks these two basic questions. And Tali's work that I referred to before is also, as I said, an important contribution in this endeavor. Okay, so I want to talk a bit more about the problem itself, and then mention some of our works in this context, just to give a feel for the different things we're thinking about. So I will talk about both optimization and overfitting, but somewhat more about overfitting. So let me define that a bit better. So again, here I'm talking about a regression problem where you have points x and output y, and you want to learn a mapping from the function from x to y. Okay. So again, because you have a network that has so many parameters, you can pass. There are many ways of fitting a network to this data. There's this nice smooth function here, but there are other wiggly functions that also will give you a zero training error for this data. Okay. Okay. So again, this begs the question: how can you hope to generalize if you know for this point you can fit any functions that fit the data can give widely different values for a point outside the training data? How, in what sense can you even talk about generalization? So in a way, you can't. I mean, if all you do is return a function that fits the data in this context, you will not generalize. You could fail miserably on data outside your training data. Okay. So in a sense, the only way to avoid overfitting is if your learning algorithm, the thing that you use to learn, doesn't just choose an arbitrary function, okay, but it chooses among all the functions, the possible functions that pass through these points, it chooses some nice function, okay, some functions with some added property. And of course, you also need reality to satisfy this nice property, okay? So for example, smoothness is an example of that, right? So if I were to choose the smoothest function that passes through these points, then it's if this is real data, maybe it's not unlikely that this is a better model for this data than all these wiggly functions. Okay, but in a sense, for generalization to succeed in very large models, you need something else. You need your algorithm to choose to have some criterion for choosing among all these functions and to choose some nice function. Okay, for example, there are many examples of what nice could mean, but smoothness is just one, right? And in the context of deep learning theory, this is referred to as the inductive bias of the algorithm. Namely, you have an algorithm that learns, okay? It gets the data, it returns a model, and this algorithm has a bias towards certain functions, okay? If it doesn't have a bias, if it can just return any arbitrary function that fits the data, then obviously you cannot generalize, okay? So this is going to be a key element or key object in this talk is this notion of an inductive bias of an algorithm, or specifically the algorithm that we use for learning in deep learning is stochastic gradient descent or just gradient descent. So we and many others are interested in the inductive bias of the SGD, namely, what are the functions that SGD thinks, quote unquote, are nice, okay? So if you learn these 5 points with SGD, what function will it return? What properties will that have? Okay, because this is really what we want to understand in order to understand this issue of generalization. Okay, so let me show that graphically. So what does optimization mean? It means that we start with some initial point. Okay, so this is initialization, and then this blue thing is the parameter space of the network. And then SGD, our optimization algorithm, takes a path through this space where we keep reducing the error until it gets to something that has low error, let's say 0 error, okay? Now, as we said before, there are many models that have 0 error, right? There's this red ellipse here, contains all the models that have 0 error, okay? And gradient descent will find one particular model, okay? And not some other. We really want to understand what is special about this model that SGD finds, okay? In what sense is it maybe simple, which would maybe explain why we have good generalization, okay? So again, the question of inductive bias of SGD asks which functions, how can we characterize the functions that SGD converges to out of all the functions that fit the data? And this has been extensively studied. I mean, also before deep learning, but I would say more intensely in the last 5 years or so. There's this very nice paper that observed this phenomenon, put the spotlight on this issue of the implicit bias or inductive bias of the optimization algorithm. It's a paper called The Rethinking of Generalization. And there's been a lot of work on understanding this exact problem. Okay. And I didn't say it, but it should be obvious that how you initialize also plays a role, right? Because if I initialize to some point in the red ellipse, then I will not have any bias. I will just stay there, right? So initialization should also play a role. So we're trying to understand the inductive bias of both initialization and the optimization algorithm itself. Okay. Right, so let us try and formalize the problem a bit more and say what people have done. So the question is, which parameters or functions does SGD converge to? You give it some training data, you initialize from some point, and you want to understand out of all the functions that it could fit the data with, which one will it converge to, okay? There are many candidate answers with some work along each of these. So one prominent line of work says that will converge to the parameters that have minimum norm subject to some constraints. And there's quite a bit of work on that with very nice theoretical results. Okay, so it sort of says you have network weights. So we'll try to find the model that has the minimum weights out of all the models, minimum norm of weights out of all the models that fit the data. A related notion is smoothness, which I alluded a couple of slides ago, which says this intuitive thing that you might think that SGD tries to find functions that are smoothest, okay? And it turns out there's a very close connection between the norm of the parameters and the smoothness of the function as measured by, say, the derivatives of the function. Another related concept is rank, the rank of the weights of the matrix. There's quite a bit of work on that, suggesting that in some cases, if you learn with gradient descent, it will try to minimize the rank of either the weight matrices or the mapping between input and output. And again, this is some notion of simplicity. And there's work that I'll describe here that we did where we show that in some cases, gradient descent does this smart thing of actually collapsing weights wherever it can. Okay, so just trying to find the most compact, simple network that it can to explain the data. Okay, I forgot to mention here, but there's more work on neural collapse by Donahoe and colleagues, which is also maybe in this vein. Okay, let me give you a simple example where this phenomenon of inductive bias of SGD or gradient descent is already evident, and that's actually, it's very easy to see formally. So let's think about the problem of just linear regression. Okay, you have a data matrix X, so each row here is a data point, and you have a weight vector W, where we have more parameters than data points. Okay, so we're in this over-specified regime where there are many possible solutions to this regression problem. Okay, because it's over parameterized. And let's see what SGD would do in this case. Okay, and I want to show you that even in this case, it's easy to see what is the inductive bias of SGD, namely what solutions does it prefer. Okay, so if we do regression on this, we basically want to solve this quadratic minimization problem, right? We have, this is the output of our model, w.h.p, yi is the desired output, and we want to minimize the square error between those. Okay, and in this case, we can certainly minimize it to be 0. Okay, and there are many possible solutions because there's this null space that we can play with. So let's say we use gradient descent to optimize this, to minimize this function. Okay, and we start out from 0. So what will happen? The gradient of this function is, you know, if they take the gradient with respect to W, you just get some linear combination of the xi's, right? So this says that if you optimize using gradient descent, your weight vector that you learn will, oops, sorry. Oh, yeah. The weight vector that you learn will be in the span of the data points. Okay. Now recall that you don't have that many data points. Let's say you have 20 data points. So this means that if you learn with gradient descent, the learned weight vector will be in this 20-dimensional linear subspace. Okay. Out of all this W space, it'll be restricted to this 20-dimensional subspace. So you already see this beautiful simplicity of this algorithm, that it can't do anything. Okay, it has its own way of optimizing, and this is where the simplicity of its solution comes from. Okay, right. So now it turns out that there's only one point that both fits the data and is in the span of the training points. Okay, and this weight vector is precisely the one that has the minimum norm out of all the weight vectors that fit the data. Okay, and that's fairly easy to show. Right, so this said that if gradient descent converges to a zero-error solution, which we can prove it does in this convex optimization case, it will actually converge to this solution. So this says that, at least for this example, gradient descent's notion of simplicity, the functions that it likes, the weight vectors that it likes, are those with minimum norm. Okay, so there you have it, right? This is a result on the implicit bias of gradient descent for this setting. Okay, and something similar in spirit happens also when you turn to more complex neural network models. Okay, all right. And there are also results. I don't go into it here, but there are also results that say that if you manage to learn a function with low norm, you will also generalize well, right? So this is the nice aspect. So if you have data that can be fit with a low norm weight vector, you will find that a low norm vector, and you will generalize well to new data. Okay, so this is sort of an intuitive explanation for what's going on. Right. So just to summarize, this simple observation says that gradient descent does sort of implicit L2 regularization. In a sense, it's actually explicit, right? It's implicit because you don't see L2 regularization in the gradient descent updates, right? But it's in there in practice. Okay, so you run a gradient descent, it'll just find the minimum norm solution, which is somewhat surprising. Okay. This is for regression, and Sudri and colleagues have shown this also for classification, a result of a similar nature. Okay, I'll mention some of that later. All right, so this was some background, and I want to now talk about some of our works in this problem region. So I'll talk about a few works of ours. Right, so first work is with Alon Brutzkus, my PhD student who is now graduating. And we asked, again, this question of why do large models generalize well, okay? And we focused on this very classical problem of XOR. It's a classic problem in neural nets as well. It highlighted the limitations of linear classification, has a long history from Minsky and others. So certainly, a basic problem to look at. So this is the XOR problem. You have 4 points, XOR in 2D, okay? You have 4 points, 2 are labeled plus, 2 are labeled minus. This is not linearly separable, right? So you need nonlinear separation. And we started out asking, what happens if we use neural nets to learn a neural net to learn this problem? Okay. Right, so we looked at the following neural network. Let me show you here. So we actually have just 2 inputs. So just imagine 2 green circles here. We have a hidden layer where each neuron here is a linear transformation of the inputs. And we fix the output weights have to be +1 and have to be -1. Okay, so we denote the neurons with the negative output weight to be UI and positive to be WI. And with the nonlinearity here is the ReLU function. Okay. So obviously it's a simple problem to solve, right? It's just a simple problem with 4 data points. And it turns out you can see it that you can solve it by using a network with just k equals 2, namely 4 neurons, where each neuron essentially points to a data point. And the negative neurons point to the negative data points, the positive to the positive. Okay, so here's a sort of a solution to this problem, right? But the network, of course, doesn't know the solution, right? So now let's say you take a network, you take k to be 1,000, and you train it. Okay, you show it these 4 points, and you say, network, please find parameters that fit these 4 points well. And surprisingly, when we looked at this, even the question of whether a network can converge to a correct solution, namely something that has 0 error, it wasn't clear how to show, because this is non-convex optimization problem, and there are many technical hurdles. So we wanted to first understand whether optimization is possible and what happens during optimization. So let me show you what happens, which we thought was surprising empirically, and then we also provided theoretical results to support. So in these figures, recall this is a 2-dimensional problem. The input is 2-dimensional, so each weight vector is a 2-dimensional vector. And what I'm plotting here is the negative vectors and the weight vectors with negative output in red and positive output in blue. And this is just the initialization. Okay, so this is how I initialize. We initialize randomly, so you have this nice, distribution of vectors throughout space. Okay, so this is a large network. I think a few hundred neurons here, and you see that the neurons explore space well, right? So there's sort of for every direction in space, there's a neuron that points roughly in that direction, and so we call that exploration features. Okay. So the initialization explores the possible features or possible directions in space. Okay, so that's what happens in initialization. And now when we train the network, look at this beautiful thing that happens. Okay, so the network finds these 4 correct solutions. It didn't have to find these, right? It could have fit the data in a manifold of different ways, right? But it chose the elegant path, right? So what happens is that neurons just get clustered. Okay, they converge to 4 groups of well-clustered neurons. Okay, and this obviously also fits the data well, because it's it's almost like the solutions that we knew should work, right? So this demonstrates 2 things. First is that if you initialize with the wide enough variance, you explore all the directions that you will probably need. But then something else happens where there's this clustering of weights, and the network finds the simplest solution, which we thought was really interesting. Now, I just wanted to say, when you use a small network, in this case, k equals 2, what happens is that you don't get this exploration effect. So it's not unlikely that you initialize to something like this, and then you under-explore, essentially. And then when you optimize, you'll fail. Okay, so even though you could, there is a solution that uses just 4 vectors, you're not going to find it because you initialize badly. Okay, so this shows you the power of large networks. On the one hand, initialization, you have a lot of degrees of freedom. So if there's something interesting, you'll probably find it. But there's this second effect where the network converges to simple solutions. Okay, and these 2 things together should give you some intuition as to why these things generalize well. Okay, and because there is some inherent tendency towards the simple solution. In this case, a solution where just neurons do the same thing if they can. All right. So we did prove essentially that this is what happens. Okay, we proved that for a large enough network, not that large, 16 networks, 16 neurons, the network will converge to a good solution, and the solution will be clustered. Namely, you will have these 4 clusters of neurons. So we could show that. The analysis relies on essentially first showing that because you have sufficiently many neurons, you'll explore space well enough. So you'll have these 4 directions in the potential of your weights. And then we had to follow the optimization trajectory rather carefully to see what happens to these neurons that are initialized in these 4 regions of space, and that they are pushed in some way that results in this clustering. Essentially, you can think of it like all the neurons that are agree on something in the beginning will tend to be pushed in the same way by the same inputs, and this is why they cluster. Okay, so from some point on, they have the same fate, and then they just experience the same dynamics, and that this is sort of where the clustering comes from. Right, so this was sort of the simple XOR problem, which was nice to see what happens there. But we also studied an extended version of XOR that's high dimensional, sort of made up of small XOR problems. And we saw that the same thing happens there. I won't go into the details, but this is just to say that the same phenomenon happens for high dimensional problems, the same phenomenon of clustering. And there we can show that this is a direct result, implication for generalization. Okay, which should be intuitive. I mean, if your learning algorithm knows to find these simple solutions, then for generalization, that's certainly good, right? Because instead of these hundreds of neurons, you essentially just have 4 effective neurons, and then your effective number of parameters is not that large. Right. One thing that is also natural when you look at these clustering of neurons is that you can say, okay, I can take this network that has hundreds of neurons and I can actually turn it into a network that has just 4 neurons. I can compress this network, right? Because many of the neurons are just redundant. So we did that, and that actually works quite well in practice. Okay? So, just as a practical side note, if you have a network, it's worth exploring whether there's this type of redundancy, because it can result in smaller models. Right. So that was this work. So then we got intrigued by this question of clustering, and I want to show you another sort of setting where it comes out. So in this setting, we actually, in terms of sort of the teacher model, namely the thing that generates the training data, we consider the simpler teacher, where the data is just linearly separable. So just you get the blue points and the red points, and there is some linear separator between those. Okay, so something that you can certainly solve with the perceptron, not a big algorithmic problem if this is just what you want to do. But what we wanted to ask was, in this simple case where the teacher is a simple function, what happens if you train this huge neural network to try and learn this rule? Right? It's not clear at all. It's not clear that you will optimize, that you will find something that separates, right? Because there are local optima and all these bad things. And it's also not clear that you will generalize well, because maybe you'll find this very funky function that somehow separates the blues and the reds, but doesn't at all look linear. Okay, so not at all clear what to expect. Okay, yeah. So we focused on learning this with a large neural net. Here we use the leaky ReLU activation, which is like a ReLU, but instead of max with 0, it's max with some low slope function and z. And we minimize cross entropy loss, which is the standard thing that people do when learning classifiers. And we ask what will happen. So let me show you empirically what happens, and then some theoretical support of that. Okay, what are the key questions? The first is, as I said, the question of optimization. Can the network trained on this find low training error solutions? And the question of inductive bias, namely, if you train with SGD, which functions will it learn? Let's say it does fit the data, but how will it fit the data? Okay, so let me show you what happens. So if you use SGD, but with large initialization weights, this is what happens. Okay, so you learn something that fits the data. Okay, but it does this with this semi-funky, separator. Okay, not that certainly not linear. And when you look at the neurons, okay, this is 2D, so each neuron is just a vector in 2D, and here we just look at the direction of those. They're well spread out across space. Okay. Now, what happens when you use small initialization? This is the decision boundary. Okay, so this is pretty amazing. This boundary, this function, is a result of more than 100 neurons. Okay, so it's not a linear function. It's a sum of 100 neurons, but it just happens to look almost perfectly linear. Okay, and when you look at the neurons themselves, you again get this clustering effect. Okay, so there are the same number of lines here as in here. Okay, but they just collapse on each other into 2 different lines. Right. So again, you see this beautiful notion of simplicity in gradient descent learning, where here it also depends on the initialization. But when you initialize small, this network finds really the sort of the simplest possible thing. Okay. Also, both in terms of the function itself, but also in terms of the implementation of the function. Right. So it really uses just essentially, effectively, 2 neurons to model this function. Right. So we thought that that was quite interesting to understand why this happens. Okay, so in terms of what we observed, the linear, okay, another interesting thing is I showed you this linear decision boundary. So this is after you take the sign of the output. But before you take the sign, you might say, okay, it's probably just a linear function before the sign. But actually, it's not. What happens if you look at the function before the sign? This is what it is, okay? So it's a nonlinear function that has a linear decision boundary. I think that's rather interesting, okay? And then the reason is that you had these 2 neurons that were not, these 2 effective neurons were different, okay? So this is this difference of these 2 neurons, and it's not a linear function. Right, but its sign is linear, okay? So that's another interesting empirical observation. So here are our main results that go some way towards explaining this, and I should say it's not a full explanation. There is an open problem here that I'll mention later. In terms of optimization, we could show that SGD, if you train it, it will find a classifier with arbitrary low error epsilon in this many iterations. So optimization we can show works. Namely, if you run SGD on this data, it'll find a 0 or error solution because the epsilon can be arbitrary. So optimization is essentially okay. For inductive bias, that's what I meant. We don't have the full picture. What we did show first was that if you have this clustering of neurons into 2 clusters, this does imply that the linear decision boundary will be linear. The implied decision boundary will be linear. So if you have 2 clusters of neurons, this will generate a linear decision boundary that we can show. And empirically, from experiments we did, we find that neurons are indeed clustered in this way. So that's good. And then we could also show that under certain conditions on the trajectory, if you optimize using gradient flow, which is this continuous version of gradient descent, it converges to a clustered solution. Okay. So the overall story here is that under these conditions, which I'll mention later, if you optimize with gradient flow, you will reach a linear decision boundary. Okay. But the reason I said it's open is that these conditions are, we'd like to get rid of those because they are quite strong. Okay, so for optimization, the question is whether SGD will find something that has a low error. And we showed this, and the idea is to use this perceptron proof with some adaptation for the nonlinear case. So we did something similar in earlier work, but we had to further adapt that to this cross entropy case. And we did this particular analysis for SGD in this setting to bound the number of epochs that are bad. And then we could show that you cannot have too many passes over the data such that the loss is large. Okay? And that essentially proves that you converge to low error. Okay, so that's in terms of optimization. What about the implicit bias? So as I said, the first result says that if you have neurons that are almost or clustered into 2 distinct clusters, then you will have a linear decision boundary. Okay. Again, that's not clear because you have a neuron network with 2 neurons, so it can implement nonlinear functions, but in this case, it has to implement the linear function, which is somewhat non-intuitive. But we could show it, and this is essentially the lemma that does it. Okay. And interestingly, this holds for leaky ReLU, but it does not hold for ReLU. Okay, so ReLU has a slope 0, and leaky ReLU has a slope that's non-zero. So this is a leaky ReLU network with 2 neurons, and if you take a ReLU network with 2 neurons, it doesn't have this linear decision boundary. All right, and we empirically validated that neurons, as I showed you a few slides ago, that neurons do tend to cluster nicely. Okay, now you could ask why does SGD converge to this 2 cluster solution? So I want to describe the result that we do have with that. And it says that under some conditions, gradient descent will converge to 2 clusters, and the conditions are as follows. They say first there exists an iteration with a small enough loss. This is something that we did show for gradient descent, but not for gradient flow. But I think this should be possible to show. The stronger assumption says that from some point on, all the W neurons, namely the positive output neurons, agree on the way that data should be classified. And same for all the new neurons. What do I mean by that? It means that all the weights classify the data in the same way. Okay. So all the points that are on the positive side of one neuron are on the positive side of the other neurons. So they agree. So if the condition says that from some point on this is true, right? Of course, it would be nice to actually show that this holds, but under this condition we show what we show. And here, for example, there is no agreement, right? Because this green dot here is on the positive side of two half spaces, but on the negative side of this. All right. But we did verify that this happens for example, for Gaussian distributions of input, that this agreement does happen. Right. So if you have under these conditions, we showed that you will converge to this two-cluster solution. The idea is that gradient flow has been shown by others, by Liu and Li, converges to a KKT solution of the maximum margin problem. And that KKT condition implies perfect clusterings if the neurons agree as an R condition. Right. So that's essentially the result. So it gives some support or of this understanding under which conditions you will get this clustering phenomenon. I should say we did have, because we were very intrigued by this clustering phenomenon, we did experiment with other settings like nonlinear rules, for example, learning logical formulas. So here are some results in this case. So each row here is a neuron. So we have like around 700 neurons, you have 100 variables. And when we learn these logical formulas, you see again this very nice collapse or clustering of different neurons. So this seems to be something that holds more generally and rather challenging to prove formally. Right. So I'll go briefly over two other works with slightly different flavor. Less clustering, implicit bias, and more sort of norm of the parameters. So in the first, we look at this very large, an important class of problems where you want to detect patterns in input, right? If you think about the visual input, visual system, it's something basic that it does, right? It tries to detect patterns in the visual field. So in a pattern detection problem, you have some classes, let's say flies and birds, and you would like to detect those, okay? So what's a natural way of doing that is to have some local detector, run it over the entire image and look for a particular pattern, right? So for example, I could look for the X pattern if I'm trying to identify an 8 figure. Okay, so understanding how neural nets solve these or learn these pattern detection problems is still rather open, and we wanted to make some progress on that, both in terms of optimization and generalization. So we studied this fairly simple toy model for this case, but we do think it captures some of the basic elements. So we assume that each image that we see contains patches, and these patches are orthogonal. And each class, again, like let's say fly and bird, has some pattern that is distinctive for that class. Okay, like for a bird, it would be like a bird shape. And all other patterns are spurious, namely they're not, they don't belong to any of the categories. Okay, so this does define some elements of a pattern detection problem, and it doesn't assume like white input, which is that's certainly not realistic. And so just to show you what this looks like, we have this pattern for the y equals 1 class, and this pattern for the y equals -1 class. And this is the 1 because it has this pattern, and all the rest is not. Okay, so we think it captures some of these aspects of pattern detection. So in order to learn it, we use I think the natural architecture in this case would be, which would be a convolutional network with max pooling. So you have this detector that runs over the entire image, and then you max pool to say, to ask, have you seen the pattern that you're looking for somewhere in the image? Okay. So standard CNN with max pooling. And it turns out that when you learn this, you use this network to learn these problems, you get to zero test error fairly quickly. Okay, and we wanted to understand why. And we essentially proved this, that gradient descent, layer-wise version of gradient descent converges to zero training error. And it requires only D samples in order to do that. In contrast, we showed that if you don't do gradient descent, you might need exponentially many examples. Okay, so it's important that you optimize with gradient descent, and we show that other approaches to the problem will also require a larger sample size. Right. Right. So this is the result. The proof ID basically says that the first, after a few updated iterations, the first layer already has a good representation of the input, which captures the things, the patterns that you want to detect. And other features have lower values, so you will not detect those. And we show that under this good representation, the classifier that uses the second layer has low norm, and low norm classifiers require a few examples to learn. So this is basically the idea. Empirically, we compared this architecture to other non-convolutional architectures, and not surprisingly, it works better. I mean, this is why people use CNNs for images, right? So it's, that's not very surprising. All right, so I just want to conclude with another work that we did on understanding implicit bias of gradient descent, just to give you another flavor of what these results look like. And this was I worked with Shahar Zulay, a master's student at the time, and Daniel Sudri and his group from Technion, and Natis Rebel. Okay, so again, what is this question of implicit bias of SGD, and what could be the nicest answer to it? So the question is, if you initialize to some weight and you take the SGD path, you get to some W hat. Is there a nice way of saying what W hat is? And the nicest way, many of you are physicists, the nicest way is to give some energy function that says, well, what is W hat? It's the one that has the lowest value of QW, where QW is like some potential function out of all the points in the sphere. Okay, so that would be really nice, because then Q captures this notion of simplicity. It says SGD chooses the model with the lowest Q, and Q captures simplicity, right? So that would be a really nice form of explanation, and this is what we did a few slides ago in the beginning of the talk with the regression. And nicely, in some cases, this can be achieved, and there are results by Woodsworth and Moroshko, and with Nati and Daniel Sudri and others that show this. But there are also negative results that show that in some cases it's not possible. There does not exist such a function. So it's quite an interesting question. So in this work, we went some more further with this question, and we considered the simple linear net whose parameters are u and v. So this is element-wise multiplication. X is the input. So you could think of this as sort of a simple two-layer linear network without nonlinearity. So obviously, it's equivalent to a linear function with w tilde is just this thing in brackets here. But what's interesting for us is to train both the u and the v parameters. So train it as if it's a two-layer neural net, and ask what is the w tilde that we converge to. Okay, and it turns out that you can characterize this, and you can characterize this Q function that we wanted to have for gradient descent, and this is what it is. Okay, so it says this is the notion, SGD's notion, or gradient flow in this case, notion of simplicity. Okay, so among all the weight vectors that fit the data, it will want to converge to the one that has the lowest Q. Okay, to be precise, it will converge to a stationary point of this minimization problem. Okay, but oftentimes we do see that it converges to the minimum. And it's nice, if it looks like a bit of a, convoluted expression, but if you look at it enough, it does reveal quite a bit about what is the inductive bias and how it depends on initialization and the relative scale of the different layers. Okay, so I'll just conclude. I think it's a very interesting problem to better understand optimization and inductive bias and generalization in neural nets, even in shallow nets without much depth. And the key themes here, I think, that arise from the works that I described are that large networks are often easier to optimize. This is what practitioners also see. That gradient descent is a key player in this story, in the way it finds simpler functions among all the ones that can fit, and therefore it underlies the success of these models in terms of generalization. Okay. And of course, the challenge for the entire community is to show this for progressively more complex settings that come closer and closer to real-life problems. And I'll just conclude with Tali and his theory, which I think will continue to impact and influence this community. Thank you.